Let's talk about the topological field theories. Now, this lecture is going to require you to have some prior knowledge of differential forms, of which I have already made a video on, so you could go and check that video out because I have covered the topics that you will be needing in this video from differential forms. Now, topological field theories is a very large subject of its own, but I'm going to cover some of the things in this lecture, and let me list those things out. So the things that I will be covering are as follows. The question that what does it mean to be a topological theory? So what does it mean if a theory is said to be topological? And there are two types of it. One is the Schwarz type and the other one is Witten type topological field theory. And we will look at both of those. The next thing that I will be covering is the mathematical description of the topological field and the topological field theory. And finally, I will talk about a physical example of the topological field theories. And I might be referring to topological field theories with TFT, right? That's the short form I'll be using for topological field theories, right? So let's actually start with the question that what does it mean to be a TFT? What does it mean to be a topological field theory, right? Okay, so well, of course, it's a theory, and if you've been watching my videos, you know that for a theory, we must include its degrees of freedom and their interactions. Now, a part of specifying degrees of freedom is to providing the space-time upon which these degrees of freedom are going to do their thing. Now, in specifying a space-time, we have almost two independent features, right? So to specify a space-time, the two almost independent features are first one is geometry. Geometry. Okay, so in geometry, we talk about there is scale, right? And that means that if you stretch the geometry, it will change it. Then we have distance, and we have this property of local. Now, what does that mean? That means you can mess with things that are far away, and yet you can preserve the geometry in the neighborhood, right? Now, geometry is usually described by a metric, right? Described by a metric. Now, a metric is something that gives us clocks and rulers to define distance, right? Roughly speaking. And geometry is described by this metric with coordinates, right? Coordinates. Okay, now the other independent feature is the topology. Now, topology does not care about scale. So, does not care about scale. What that means is basically that if you were to stretch but without any tearing, it will not change the topology, right? Also, topology is global. So what that is topology cares about everywhere, all at the same time, right? All at once. Now, topology is described by it is described by characteristic classes. So let me just tell you what that means. Characteristic classes, right? Okay, that is simply sets of topological equations geometries that show common features, right? Now we will understand what that means in a bit. Now it happens that most physical theories care about both geometry and topology simultaneously. But of course, it is possible to have situations which only care about topology. Now, there are actually two ways in which one can do that. First one is with if the action, that is S, right, defining a classical through Euler-Lagrange equations, or a quantum theory, that is through path integral, it does not contain a reference to a metric. And so if that's the case, then obviously it will not change upon changing the metrics, right? Because of course there is no metric in these theories, right? If the action, if you're using action S. Now, so then the theory, in such a case, it is said to be if this action does not contain metric, right? Then the theory is called Schwarz, S-C-H-W-A-R-Z, yeah, Schwarz type theory, right? So again, if the action S that defines a classical or a quantum theory does not contain any reference to the metric, then it's known as the Schwarz type topological field theory, right? So Schwarz type theory, that is theory by theory, I mean a topological field theory, right? Okay. On the other hand, you may start with a theory defined using the metric, that is G mu nu, and if it possesses a nilpotent symmetry, if it possesses a nilpotent symmetry, that is, what do I mean by that is simply it vanishes when it is raised to some integral power, right? Positive integral power. So what I mean by that is, suppose if delta S is it is 0 with S squared is equal to 0, right? And then one can demonstrate a class of its correlations functions or its metric indices, right? And these type of theory is called Witten type topological field theories, right? So Witten type TFTs, right? So after all of this, the next natural question is then, what does a topological field theory looks like? So for that, we are going to consider consider electromagnetism in a 4-dimensional manifold, right? So M4. Now, if you have watched my videos on electrodynamics in special relativity, right? So relativistic electrodynamics, you might recall that the action is for electrodynamics, electromagnetism is -1/4 integral d4x F mu nu F mu nu, right? Right now, here recall that this F mu nu is actually the electromagnetic field strength tensor, and it is written as partial mu A nu minus partial nu A mu. Over here, this A mu is actually your 4 vector potential, and it is expressed as the scalar potential V and the vector potential A, right? Okay, now if you look at this expression, at your first glance, it does not seem to incorporate a metric, right? A metric, for example, eta mu nu, right? There is no eta mu nu at your first glance, at least. But if you recall that the basic ingredient is this thing, that is partial mu and A mu, right? So this is your basic ingredient, and so then you can ask over here that what is this thing, right? So what is F mu nu? Well, it turns out that your F mu nu, the contravariant one, is eta mu lambda times eta nu beta times F lambda beta, so the covariant one. And well, if you look at this thing, you immediately realize that there is not only a metric, but in fact there are 2 of them. So we have this one and we have this one, right? Okay, so let me get rid of these funny circles. It gets actually even better, right? And that is because the measure of integration, that is this thing, d4x, comes secretly armed with a factor that is square root of negative determinant of the metric eta mu nu is equal to positive 1. And why is that good for us? It's because, well, generally what you have is a square root of negative g, which is equivalent to this thing. If you compute the square root of negative determinant of the tensor g mu nu, that is not generally equal to positive 1, right? But in this case, it happens to be that this thing is true, right? It's positive 1. And this is important to remember if we go in curved space, or we use the curvilinear coordinates on this 4-dimensional manifold, right? M4. Okay, now of course I know what you're thinking. You're thinking that why did I use this one, right? Why did I say the square root of negative g? Why this, right? Well, if you recall, under a coordinate transformation, so under a coordinate transformation, we have dx, d4x actually, which is, you can say it is x mu, that is equal to d4x prime, which you could say it is x mu prime, multiplied by the Jacobian j, where j is your determinant of partial x mu over partial x mu prime, right? Now you could also write this thing as, or d4x prime is equal to 1 over j d4 x, right? Okay, so if you look at this, then it seems like, or it means that something as simple as, say, volume is not coordinate invariant, right? But we can fix that, and to do that we simply note that the metric itself transforms as g mu nu transforms as g mu prime nu prime, right? And where this g mu prime nu prime is actually equal to partial x mu over partial x mu prime times partial x nu over partial x nu prime, right? And multiplied by g mu nu. Now this thing simply implies that you have this determinant of g that would transform as determinant of g prime, which would simply be equal to j squared times determinant of g. Or you could simply say that this whole thing is also same as saying that g transforms as g prime, which is simply equal to j squared g, right? Okay, so for all of this, finally, we can say that the integral d4x times square root of negative g transforms as the integral of d4x prime times square root of negative g prime, which is equal to 1 over j d4x, and I forgot the integral sign, so there is an integral times square root of j squared g, and I forgot a negative sign over here. There is a negative sign over here, so it's square root of negative j squared times g. I have simply substituted the value for this from here, right? And so, well, this is then simply equal to integral of d4x times the square root of negative g, right? And if you look at this thing and you look at this thing that we started with, they're the same. What does that mean? That means that this thing over here is coordinate invariant, right? And so when I said that something as simple as volume is not coordinate invariant, it turns out that with the help of this metric and the fact that it transforms as g mu nu to g mu prime nu prime, it turns out that it is indeed coordinate invariant, right? Okay, so what does this mean for the action that we were talking about? So the good old electromagnetic action is equal to then negative 1 over 4 integral f mu nu d4x, right? This was it. It depends on g mu nu, right? G mu nu is actually kind of reserved for general relativity. We could also say it depends on eta mu nu, right? And in general, it depends on g mu nu. So yes, it turns out that the action is indeed dependent on the metric, right? But what we can do from here now, right, is if you remember, or if you have watched my lecture on differential forms, which I suggested that you should, you might recall that at the end we said when we were talking about the integration, right, for the forms, we said we showed that this thing integral of a form, P form, over this sigma P is coordinate invariant, right? Let me just write this from differential forms, right? So if you have not watched that video, or hopefully if you have, or you have some idea about differential forms, you will understand what I'm going to do now, right? Okay, so over here in this integral, you recall that this AP is your P degree form, and this sigma P is your, I think I did not talk about this in that video, it is your P dimensional manifold, right? Something that you are integrating on, and that is your manifold. So it must have dimensions, and that is your P dimensions, right? Okay, so from here now, recall also that this was your case, I mean this thing, that it was coordinate invariant. I don't know why I wrote E over here, but yeah. So it was coordinate invariant because of the fact of the anti-commuting basis of forms in this thing, that is AP. It was equal to 1 over P factorial A mu 1 up to mu P dx mu 1 up to times dx mu P. Right over here, this or these are your basis forms. So I was saying that this coordinate invariant is the case because the anti-commuting basis of the forms, this one over here, right, it forms a well-defined integration measure over an oriented volume, p-dimensional oriented volume, right? So then with all of this, right, if you remember all of that, what we can do now is substitute for P is equal to 4, right? So we are taking a 4 form, and what we are going to do is we are going to let this thing, the manifold, p-dimensional manifold, be our space-time, right? Space-time M4. Now I have chosen 4p is equal to 4 because we are talking about a 4-dimensional space-time, right? Well, then I can write a new term for the action, right? So then in total, my action is electromagnetic action plus this integral of some 4 form, right? Now, well, what might this thing over here look like? That is the question. Well, we would actually like to build it in terms of, so in terms of A mu and this thing for gradient, right? And simply that's because our electromagnetic action is in terms of these things, and if you're adding something to your over here to your action, then they should be same dimensions, right, or in same terms. Only then you can of course add it to it. Now, first thing to note over here is if you recall the P forms, then this A mu are actually the components of one form, right? And so then what I can do is I can write it as A1 is equal to A mu dx mu which is simply equal to a mu partial mu, right? While on the other hand, this thing f mu nu is equal to partial mu a nu minus partial nu a mu, right? And this thing are your components of two form. And so then what I can do is I can express it in terms of this form. So that is 1/2 f mu nu dx mu dx mu. And if you cannot understand where I got this from, then you must have watched the video on differential forms, right? Over there we have this expression for writing these forms, right? Now from that video, also recall that the form components must be antisymmetric under some index exchange. What I mean by that is, if I were to write this thing, f mu nu is equal to f nu mu, right? I would have to include in a negative sign over here, right? That's what I mean by the components have to be antisymmetric. Now, also remember that the basis, again, that is dx mu should also anti-commute, right? And so one way to put that in our expression, or to remember that, is with this thing, right? So your Levi-Civita mu nu d2x, right? And so this will include the fact that the bases also should anti-commute. Now, so from here we have one form and a two form as well, right? Where again, if you forgot, this is your one form and this is your two form, right? So we have these two at our disposal, but recall also from the differential forms we have wedge product, right? And so what was that? That was, if you have your form, a P form, wedge some Q form, that would give you a C P plus Q form, right? Now, in terms of components, one can write this thing as C mu 1 up to mu P plus Q, which is equal to A wedge B mu 1 up to mu P plus Q, and yeah, and this thing is equal to P plus Q whole factorial over P factorial times Q factorial, right? And we have this A mu 1 up to mu P and B mu P plus 1, because we have already had P over here, up to mu Q, right? Okay, so now we have one option for a four form, this one, and that is simply, if you were to do this thing, take a wedge product of a two form like this, right? And so let's go ahead and do that, right? So if we were to do take this wedge product, we would have using this whole thing for the wedge product, what would we have? We have P is 2, Q is 2, so we will have 2 plus 2 factorial divided by 2 factorial times 2 factorial times F lambda beta times f mu nu, right? And then we would include this epsilon lambda beta d2x, right? And for your mu nu, we will have epsilon mu nu d2x. Right, now over here, this thing is anti-symmetric over 4 indices, right? And now let's go ahead and simplify this. And doing that, we would have 6 times 1 over 24. Yeah, and we will have f lambda beta plus f mu nu, and we would have 23 other permutations of these indices. So I'm just going to write 23 other permutations. And I'm being lazy for a reason over here, and you will quickly see that, right? Right, and then we would have this thing again, lambda beta d2x epsilon mu nu d2x, right? Now we can simplify this thing, right, by 1 over 4, right, f lambda beta times f mu nu, and we can combine these two epsilons over there, and we would have lambda beta mu nu d4x, right? And you can see that the other 23 components disappeared, right, because we combined this epsilon. So in general, your epsilon lambda beta mu nu is not equal to this epsilon lambda beta times epsilon mu nu, right? Okay, so from this, recall again that your overall action was electromagnetic action plus this 4-degree form, right? And now what we can do is we can compute this term, right? And let's go ahead and do that. So we would have 1 over 4 integral of I'm computing this term, right? We are going to include we are going to write f in terms of the 4 gradient, 4 derivative, and the vector potential, right? Okay, let me write it down so you can understand what I'm saying. d4x epsilon lambda beta mu nu f lambda beta f mu nu. This is equal to will I have space? I don't think so. Let me just write it down over here. It is equal to 1 over 4. Let me keep this here. Yeah, 1 over 4 dx d4x actually epsilon in lambda beta mu nu. And so for this, what will I have? I'll have partial lambda a beta minus partial beta a lambda, and then multiplied with this one. For this, I will have partial mu a nu minus partial nu a mu, right? And then what I can do is I can take this product, right, this one, and well, I'm not going to do it for you over here. Of course, it is just a high school thing. You have to take this product and you will get your end result would turn out to be the integral of this 4 form is your integral d4x epsilon lambda beta mu nu times partial lambda a beta times partial mu a mu, right? Yeah, a nu. Okay, so now if you look at this thing, right? This expression I think next time I will just, instead of highlighting, I'll just circle it, right? That's much quicker. Okay, so this expression over here, it does not depend on the metric, right? And you can clearly see that. But now what we did is essentially we replaced the index contraction with this G lambda mu times G beta nu, right? The index contraction with this thing by the index contraction with epsilon lambda beta mu nu, right? You can see it over here, right? So now over here, you realize the beauty of differential forms, and that is they already have the correct transformation built in, right? The differential forms, they have the correct transformation, and so we did not need this thing, square root of negative g, that we talked about. This term was not needed at all. Now, finally, from all of this, what we can do is we can consider our action. Overall action is now of the form negative 1 over 4 integral d4x square root of negative g, right? So this is the electromagnetic action that I'm writing down over here, lambda mu g beta mu, sorry, it's g beta nu f lambda beta times f mu nu, right? And now we'll write the topological action, that is this weight factor, right, for the terms, for these terms that I'm going to write down. So this this thing over here I wrote is what am I doing? Yeah, this thing is your weight factor for these terms. That is the integral of d4x epsilon lambda beta mu nu times partial times this thing, right? So it's partial lambda a beta times partial mu a nu, right? And so yeah, this is your overall Lagrange action, right? Now if you look at this right now, the theory has a topological term, right, which is this one, but it also has a metric dependent term, which is this one, right? You can clearly see your metric over here. And so then at the moment, the overall theory is not topological, right? But what we can do is consider the relative importance of these terms in certain situations. Now, for example, in quantum mechanical theories, as we consider physics at different energy scales, we find that various constants like the coupling constant, the mass of the system, and etc. Actually flow, right? And what do I mean by that is that they are functions of energy scale at which we probe the system. So the textbook values for which are the energy is approximately equal to 0. So there are technical ways to determine this flow, and this entire process of doing so is called renormalization, right? Because of course in such a case it happens to be, or it appears to be, that for example if you take an electron, it appears as though its mass is infinite, but we know, we have calculated the mass of the electron and we know it's not infinite. And so you need this process of renormalization. But one rule of thumb that emerges is as follows, that first what you do is you calculate the length dimension. So you calculate the length dimension of a term in the action. So for example, the length dimension for this partial mu is 1 over L, right? And so what that would mean is that for a mu, it also has to be 1 over L, since this d mu is actually partial mu minus a mu, right? And so you can only add or subtract terms with same dimensions, right? And so that would imply that this also has the 1 over L dimensions. Now, then this simply means, if you look at this, it means that terms with higher length dimensions are going to dominate over the terms with lower length dimensions as we consider physics at low energies, or you could say long length scales, right? Okay, so what we can do over here is comparing this thing, the dimensions of the electromagnetic action, right, which is 1 over L4, and we can compare it with the dimensions of the topological action, right? It is also 1 over L4, right? And this is something that we can verify from this expression, right? Both the integrals are d4x, right? Okay, so therefore we have both of these dimensions as 1 over L4, and what that means is that therefore both of them are always equally important, right? Both these action terms in the overall action. However, what we can do is, if I am to say consider dimensions as 2 plus 1, then the analogous story takes a turn, right? And well, first of all, what happens is that this action in this case, right, 2 plus 1 dimensions is a negative 1 over 4 integral of d3x now times the square root of minus g lambda mu g beta nu f lambda beta f mu nu, right? And this whole action is actually unchanged, right? I mean, except for, of course, your mu, lambda, beta, and nu, they go from 0, 1, 2, or they take these values, right? And also the number of components will change, right? But for the topological action, right, this one, in this this 2 plus 1 dimensions, what we require is we require something like this, so a 3 form instead of this one, right? So we don't want this thing for 2 plus 1 dimensions, we want this thing. And we can clearly see that this f2 wedge f2 will not work for us, right? This thing is not going to work, it will not do. But the simplest choice for your topological action is integral d4, we are talking about 2 plus 1 dimensions, it would be d3x, and your Lewis beta will be in 3 indices, so lambda mu nu, and we would have a lambda f mu nu, right? So that's one choice that you could, or the simplest choice that you could pick for a topological action. And from this action, what we find is that, well, if you look at least this term, you could say that the dimensions of your topological action in 2 plus 1 dimensions is simply 1 over L cube, right? And the dimensions, if you look at this, the electromagnetic action, right? They are still the dimensions of electromagnetic action are still 1 over L4. Now, well, you can say now that so in a 2 plus 1 dimensions, we find that this theory of overall action is the sum of the electromagnetic and topological action at low energies, or you could say long distances, is dominated by the topological action term, right? And what that means is that this theory in 2 plus 1 dimensions is purely topological, right? So again, you have to remember that this is purely topological in 2 plus 1 dimensions. Now, instead of ending this over here, we can go a little further and ask what would it look like, right? So what would this look like? Well, we can do one thing is we can take some electrons, right, and confine them to a two-dimensional surface and then turn on a strong magnetic field, right, that is perpendicular to the surface. So we are just perturbing our system of an electron confined in two-dimensional space, and the resulting theory is described by this thing, right, with long distance physics that is governed by the topological action over here. And this topological action is referred to as the Chern-Simons term, right? So let me actually write it down over here. This is referred to as the Chern-Simons term, right? And what this then do is, or what you can call this theory over here is, then you call it a Chern-Simons theory, right? Now, you could also then ask me, what do I calculate with this thing, right? So, first of all, since this theory does not depend on the metric, right, because it is a topological theory, purely topological field theory, it will not depend on the metric g mu nu. Then what we can say is that this energy tensor mu nu, which is proportional to your delta S over delta G mu nu. Now, because there is no G mu nu, it cannot vary with it, so it's 0, right? What this means is simply that the energy momentum vanishes. But then if this T mu nu is equal to 0, if that is the case, then this implies that the Hamiltonian also vanishes. Now, this is an awesome problem for introductory quantum mechanics. That is, to solve this eigenvalue problem, that is H psi is equal to E psi, when, of course, H is 0. Of course, you might say that the answer is equal to 0, but then that's the trivial answer to the problem. The non-trivial part is to find the wave functions psi or at least determine how many of these psi are there, right? that simply means that you're determine the ground state degeneracy. Okay, so we find that the quantum mechanical calculation in this example of the GSD, GSD as in ground state degeneracy, right? Ground state degeneracy. Right. Yeah. So, yeah. What was I saying? Yeah. So we find that quantum mechanical calculation in this example of the GSD in our system is effectively actually a calculation of topology in 2+1 space-time. Or in fact, interestingly, in a two-dimensional space part, since the time part was trivial with E equals 0. So from this, I hope you understand or you get a better insight into this topological field theories and how they're extremely useful in theoretical physics. And so yeah, this was it on in this video. I'm putting these videos in the playlist on fun physics topics. I think that's what it's called. And I hope you enjoyed as much as I did understanding topological field theories. And like I said, of course, again, this is a very huge topic of its own, and I just covered some of the interesting parts that I thought are there.